So now that we've had a chance to talk about the different categories of synchronizers in Java generally, let's take a look at the different classes that Java supports. And this is going to be an intentionally high-level overview. We will cover these classes in much, much more detail as we get later into the course, and you have a chance to play around with most of them in the assignments. So the Java Util Concurrent and Java Util Concurrent Locks packages define a whole slew of synchronizers. So I recommend you take a look at the package summary to learn what those synchronizers are. We're going to cover the core synchronizers here very briefly, and then we'll take a much deeper look at this when we talk about each of them individually for quite a number of different lessons coming down the road shortly. These synchronizers are used very heavily in Java applications, within the Java class library itself, and certain ones are really, really heavily used, and we'll focus on them, of course. One of the ones that's very heavily used is called ReentrantLock. It's a mutual exclusion lock that extends the capabilities of the built-in monitor lock, basically the synchronized keyword. And if you take a look at the synchronized semantics, they're very simple. It's basically acquire, release. That's about it. ReentrantLock, as you can see, has a couple dozen methods in it. And reentrant simply means that the thread that holds the lock can reacquire the lock without deadlocking on itself. And grad students taking the course for grad credit will get a chance to implement a RandomSpinLock in assignment 1B. Reentrant locks have to be fully bracketed. That means the thread that acquires the lock must be the one to release it, much like the restroom in a plane where the person who goes in is the person who comes out. So the person who goes in and locks the door is the same person who comes out and unlocks it. There's a variant of a reentrant lock called a ReentrantReadWriteLock, and this is intended to work for objects that are shared by multiple threads, where the object that are being shared is read from a lot more than it's written to. And a good example might be the course catalog at the Vanderbilt website, which is updated typically maybe once or twice a year, but for the most part is just read. So you can imagine using some kind of reader-writer lock on it so that you don't have to worry about corruption on the rare occasions when it changes, but most of the time you can allow many simultaneous readers who are all going to see what the current course offerings are at Vanderbilt. The ReentrantReadWriteLock that comes with Java has a blessing and curses associated with it. It's very powerful, but it's also inefficient because it's got a lot of features that are expensive to implement and actually, honestly, not really all that useful. So in practice, people typically don't use ReentrantReadWriteLock very much. Instead, they use a newer locking mechanism called a StampedLock. And StampedLock is a reader's writer lock implementation that came with Java 8 and beyond. That's much more efficient and more scalable than ReentrantReadWriteLock. Provides the same sort of capability, but it also goes a little further, and it supports things like optimistic reads, which work very well and have no contention unless there's actually sharing of some object. So if there's no sharing, if there's no contention, there's no lock overhead, which is really cool. And StampedLocks also support something called LockUpgrading, where you can attempt to atomically take a read lock and turn it into a write lock very efficiently if there's nobody else who's trying to contend for that lock at that point. There's also another important coordination mechanism called a semaphore, which is basically an atomic count that's used to control multiple threads that are trying to access a limited number of shared resources. For example, our Palantiri simulator example is a perfect example of that. We have a limited number of resources, Palantiri, and we have multiple beings that want to share them. And so as a result, we use a semaphore to ensure that only as many beings are gazing at the Palantiri as there are Palantiri. And we'll see a good example of this, which we'll talk about later, is a beach volleyball tournament where you have many courts and more teams than courts, and you have a bag full of balls that you use in order to decide which teams get to play at any given point in time. And so we'll come back and talk about that example when we have more time to discuss what semaphores do. One of the interesting things about semaphores is, unlike the reentrant locks we discussed earlier, the operations on a semaphore need not be fully bracketed. So the thread that acquires a semaphore need not be the thread that releases it. And in fact, we'll see later when we talk about the ping pong examples that they deliberately have different threads acquiring and releasing the semaphore or semaphores in order to be able to enable alternating behavior of pinging and ponging in a coordinated way. Another coordination mechanism is called a condition object, and that allows a thread to wait until some condition comes true. And it's typically used if you want to wait for multiple things to happen before you can go ahead and proceed. And so an example, which we'll also talk about in more detail later, is delivering pizzas, where you've got a group of people who are delivering pizzas. And in order to deliver a pizza, you have to have the keys to the delivery truck and a pizza. And you have to have both of those resources before you can deliver the pizza. And the threads will compete to see who can get the keys and the pizza. And if you don't get that, then you have to go back to sleep and wait for a chance to do your delivery later. And I'll talk about that example. You don't have to worry about knowing that example yet. We'll cover it later. But it's another very powerful coordination mechanism along with semaphores. Condition objects are always used in conjunction with a ReentrantLock. So they come together, and there's a factory method on ReentrantLock that actually returns a condition that's used with that lock. And I'll explain why we need that later. The last few synchronizers we're going to talk about briefly here are the barrier synchronizers. There's something called a CountDownLatch that allows one or more threads to wait on the completion of operations in other threads. A good example would be a group of people who go through a museum with a tour guide, and the tour guide might say, I'm going to wait for all the people who've registered for this tour to show up before I take them on the tour. So as each person shows up, we count down by one, and when they're all there, then the tour can start. So it's kind of like another example of a starting gate for a horse race or a sprint. There's another form of barrier synchronizer called a cyclic barrier that allows a set of threads to all wait for each other to reach a common barrier point. Good example for this might be an assembly line where you have groups of construction workers or assembly people who wait for the vehicle to roll up, and then they all work together, putting on the appropriate parts, the tires or the transmission or the drivetrain or the engine or the windshield wipers or whatever they do. And when they're all done, they all step away. The next car rolls forward. They all come in to work together on that particular job, that particular task. So it's cyclic. Each time a new thing comes along, and they all coordinate their actions. And then the final type of synchronizer, barrier synchronizer we're going to cover is called a phaser, which is a more flexible and more dynamic way of being able to do things like cyclic barriers, where you don't have a fixed number of parties who are doing the tasks. So the example here might be something like people who are building a house. You might have people who come and put up the frame, and there's maybe 7 of them, and they wait till they all show up to start work. Then after the frame is put up, you might have a bunch of people who come along and do the wiring or the plumbing or the roofing or the bricking or whatnot. And there may be different numbers of work crews who have to coordinate to do their task. So a phaser gives you a more dynamic and flexible way of coordinating different groups of threads that work together in some common goal. So that's the end of the quick overview of Java synchronizers. As you might imagine, there's a lot more to it than we've covered here, but I wanted you to have kind of the big picture view, the kind of the forest view of synchronizers before we start diving into each of these classes, into the trees, and look at them all in more detail.